time to start.
All right. Day 10. Let's see what we got. Oh, share the screen. Turn this off. There we go. Zoom. Day 10. You all arrive at a lava production facility. Okay. The reindeer is holding a book entitled Blah. However, when you open the book, you discover this. It's a blank topographic map. Perhaps you can help fill in the missing hiking trails. The topographic map indicates the height at each position using a scale from 0 to 9. Okay. So that's a valley, and it slopes down from here down to there. This slopes down this way. Okay? Based on unscorched scraps of the book, you determine that a good hiking trail is as long as possible and has an even gradual uphill slope. Oh no. For all practical purposes, this means that a hiking trail is any path that starts at height 0 and ends at height 9 and always increases by a height of exactly 1. Hiking never includes diagonal. Okay, so taxi cab only. Only up, down, left, or right. You can look up from the map and notice that the reindeer has helpfully begun to construct a small pile of pencils, markers, rulers, compasses, stickers, and other equipment that you might need to update the map with hiking trails. A trailhead is any position that starts one or more hiking trails. Here, these positions will always have height 0. Assembling more fragments of pages, you establish that a trailhead score is the number of 9 height positions reachable from that trailhead via a hiking trail. In the above example, the single trailhead in the top left corner has a score of 1 because it can reach a single 9. This trailhead has a score of 2. This one has 1 because it can go 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, 1, 2, 3, 4. Oh, no diagonal. Right, so, 1, 2, 3, 4, 5, 6, 7, 8. So this has 2 ways to reach the same 9, but it's the same 9, so only 1 point. Okay. Wait, where was I? Okay, this is 2, yes. The positions marked with dot are impassable tiles to simplify these examples. They do not appear in your actual topographic map. This trailhead has a score of 4 because every 9 is reachable via a hiking trail except the one immediately to the left of the trailhead. Right, can't go 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. 4, 5, 6, 7, 8, 9. 4, 5, 6, 7, 8, 9. Okay. This topographic map contains 2 trailheads. The trailhead at the top has a score of 1 because it can reach 5, 6, 7, 6, 7, 8, 9. So it can go up and down, but only by 1, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This should be 2. The top has a score of 1. Oh, no, it cannot go up and down. Uphill. Always increases by 1. Okay, so no, it can't go down. So this is not impassable, but not desirable, right? It's this cycle right here. Okay, so we can only reach this one, but this one can go 7, 8, 9, 6, 7, 8, 9. Got it. And a full example. The reindeer gleefully carries over a protractor and adds it onto the pile. What is the sum of the scores of all trailheads on your topographic map? Let's see what would be. Okay, this looks memory loadable. Straightforward enough. Let me zoom in. Nice big. Are we connected to a REPL? We are. I was playing with some interrupted stuff this morning. Or the other morning. Source 2024 Clojure namespace day 10. Oh yeah, by the way, Norman, aka Maximo Burrito, was able to find the bug in my original part 2 of 9. Check it. It's so tiny. Wait. This... Yeah. I think, yeah, both of these. Small, teeny tiny changes, though. This one was Inc. C prime, which is almost reasonable, but not correct. This is obviously supposed to be count of EIs. And then we had to change this check. But it was very small changes that needed to be made. It was mostly correct. It's unfortunate. That's how it goes. That's how it goes. Okay. Hang on. Okay. Get my test input. We're gonna make a parse. Stir. Split lines. We kind of want to turn them into numbers. We could leave them as characters, but we do want to turn them into numbers. We remembered last time. What was it? Okay, I thought I remembered day 9. Nope, wrong day 9. Character digit. Okay, so we should be able to parse this now. Boom. Easy peasy. Right, so this is a tree traversal. Can it start at any 0? Or does the 0 have to be on the edge? I forgot. Always have height 0. See, all their examples have 0. Another thing I need to mod, and I don't know how to mod. Wait a minute. Wait a minute. Hang on. I think I lost. Let me look at something real quick. Okay, yeah, we do have 2 viewers. Well, one might be me. May not have any viewers, but I can't see the number of viewers in OBS anymore. And I don't know. I forgot how to do that. Notes only, follows only. Oh wait, no. Docs. Chat. And then stats. That's it. Stats. No, not those stats. Twitch activity feed? No. Forgot how to do it. Stream information is there. It's not stats. I don't know. Well, I have no idea how many people are in chat anymore, which is mildly irritating. Oh wait, is it somewhere? Nope. Whatever. I'm just gonna carry on. Is it Twitch stats? Oh, there it is. All right, all right, all right. We're good. I can see again. I can see. Oh, wait, I want it right here. Oh, we have like a good number of viewers. I thought I was streaming to no one, which is okay. It's okay if y'all are busy, but we do have 5 people, which is cool. Okay, back to where we were. Oh yeah. All right. So we have this map. All right, so we have a tree we need to traverse. Is what the long and the short of this is, right? Like well, the one thing I'm not sure about. I don't know if anyone in chat knows. Do we have to start on an edge, or is every 0 eligible? Because like in all of their examples, the 0s are on the edges. It says 9 trailheads. Let's see. 1, 2, 3, 4. No. Every 0. Yeah. Okay. Okay, so we need to look for 0, and then we need to recursively just search, right? And you can only move if the number is 1 greater than where the number that you're on, right? And there's a way to do this with tree seek, right? Because you can make a tree out of this. But I'm not really great at using tree seek, if I'm honest. It is not my forte. Let's try it real quick. Right, but you would want multiple routes. You want to use this as the backing data structure. Let's call that B for board. But you want to just start, one route is like here. So let's just hard code in a route real quick. 0, 0, 1, 2, so 0, 2, right? That's a route. And the children is a fun, and the branch is a fun. And so this is a function that takes position and will return, I don't know, I almost typed return as I was saying return, which is not a thing in Clojure. We have a thing in util, taxi cab neighbors for this board for this position. right? Let me zoom in. Which does work, but ends up giving you the up, down, left, and right as long as it's in the bounds of the board, right? We want to remove. Let's see, our current value. Get in the board, our position. We want to say filter. Pause prime. We want to filter where get in V prime and ink V, right? Get in board pause prime is equal to V prime. So we only want the ones that are one increment of the value. And so this will return a list of children. It doesn't have to, we don't have to do it like this though. It doesn't have to be eager. This is fine. This will return a list of children. So it won't return this, right? 0, it won't return this position, but it will return this one and this one. And then, oh, what does this take again? The branch function. One arg returns true if the node can have children, but may not. That feels like an optimization I'm never sure what to do with. Let's do constantly true. Like they can always have children, potentially have children, right? Bring in util. Well, this is kind of it. Maybe. Let's see. 0, 0, 1. It shouldn't go to 0, 1. Yeah, but it goes to 1, 0, 1, 2. It does go here. And then it should go 1, 0, 1, 2, 3. 1, 3. Yeah. So the path is there. But it's not grouped at all. Well, I mean, I guess it is the path for this starting position, right? In fact, it's all the paths for this starting position. Hang on, let's see what happens here. It's pause P. Let's just return P, get in board P. One, two, three, four, five, six, seven, eight, 9. Hang on. From 549 to 349. What is that? 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 5, 4, 9. 0, 1, 2, 3. 0, 1, 2, 3, 4. I wonder how that happened. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, and then the next one was 8, 9, and then there's another one. 8, 9. Oh yeah, 3 all together. Is this right? Can I just find all, like, count the number of 9s? Surely it's not this easy, right? Filter. I didn't want to do that. No, 20 is too much. Oh, we need to distinct it. Like if it can reach the same thing multiple ways. Don't worry, team. I'll fix this up. 5. 5. 5. Okay. So the only thing we have to do after this is find all the zeros, because I hard-coded in a 0 here. Clean this up so it's not crazy. And we're good for part 1, right? Let's just hard-code all this into part 1. We need to map. Let's see, how do we find? Here we go. Util board rect points of the board, right? Map cat. Point P. 0, get in NP. So only find, oh, not map cat, it's just map or filter. Filter. So just find the 0 points on the board, right? Map. Cat? Map? I don't know. This is the route that we're passing in here. Okay. So for that route, walk it. And I mean, we don't really need to return anything. Here, except... yeah, we want a distinct here, for sure. Filter. Filter where this value is 9. We only want the ones that equal 9. Right? And we want to distinct those points. Now we have a list of points. We have a list of points that are the 9 points that we can reach from this root node, right? Map cat those, I think. But we want to distinct down here because it's distinct per root node, right? Not per... like, you can have 2 root nodes pointing to the same thing, right? So we want the distinct to be right there. I think this is a potentially valid solution as it stands. Let us see. Oopsie. We say 36. The answer here is, in fact, 36. Hey. I mean, okay. I don't want to get crazy. I don't want to get crazy because part 1 of day 9 was like really straightforward too, right? It wasn't it wasn't that bad. It was part 2 that was the problem. Let's see. The reindeer spends a few minutes reviewing your hiking trail map before realizing something, disappearing for a few minutes, and finally returning with yet another slightly charred piece of paper. The paper describes a second way to measure a trailhead called its rating. A trailhead's rating is the number of distinct hiking trails which begin at that trailhead. For example, the above map has a single trailhead. Its rating is 3 because there are exactly 3 distinct hiking trails which begin at that position. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. Okay, but these are explicitly the things that we filtered out in part 1, right? Part 1 we said distinct. Jealous how easy it was to do the tree walking there. I did all mine from scratch. Yeah, I mean, that crossed my mind. It crossed my mind to do either a breadth first or a depth first search here. I don't think it matters which one you choose for this one because it's not so big that you can't just do it. But TreeSeek, I mean, you heard me say at the beginning, TreeSeek is like kind of wonky to use, but once you figure it out, it's super, super straight. It's super nice. Super nice. Okay. Right. Here is a map containing a single trailhead with 13. Right, I'm assuming it's the same thing. That one's 227. Blah, blah, blah. Here's a larger example. I mean, is it? Am I? I'm missing something because I don't think I got the right answer. But like my initial, like having, yeah. I mean, I saw what my previous answer was, but I forgot about it. But having done it once, it's not just this, right? It's not just, hey, don't distinct it. Don't distinct it. Look at all of the ways that you can reach a 9. Look at all of the ways that you can reach a 9. Is that? There's no way, right? Oh man, this bug. That bug in IntelliJ. There's no way, right? Oh man. After day 9 part 2, honestly, after day 9 part 2, I feel like I deserve this. I feel like this is a much deserved win. Like they owe it to me for real. And I appreciate it. I appreciate the easy win. You know what? Because it was so easy. We'll make a helper function so it looks better. Board or N, right? Okay, I guess I'm gonna try TreeSeek on some AOC. Yeah, no, Maximo Burrito. TreeSeek is the AOC way. Like I only ever use it in AOC, but it is so useful in AOC. Like it's kind of dumb how useful it is. What do we call down here? A path XF, right? That's what we want. So we'll pop in path XF here. This is the power of the X form, folks. Right here. Check it. It's computation passable. It's just a function, right? But this will be walk in with distinct. Only take the distinct paths right? Count. What do we call this? Trails? Trails? Something like that. Oh, yeah. No, that returns the trails. That's correct. Okay, yeah, and then this one's going to be count trails in... Not trials. Although this is a trial and a tribulation, but it's not that for this. Just a no-op, right? And in fact, we can simplify this a little bit. I do this quite often. Trails, not trials. Make it a little easier to use. Identity. Bom bom. And now we don't have to pass it in. We know it's okay to use like this. Part 1 was 535. Part 2, syntax error. No, 1186. We are good. Woo! Only 30 minutes. ...2024, day 10... ...in the books... Do I try day 11? No, I think day 11 is a mistake. I think it's a mistake to do it now. Oh, no. Day 11 is not that bad. Its part 2 is a little harder, but my part 2 was so easy. Okay. Let me pause real quick. I gotta use the bathroom. I didn't go before the stream. So let me pause, and then I'll be right back, and then we'll do day 11. All right, give me 1 second. Give me 1 second. Day 11 was pretty easy. Okay, good. Maybe I can do it in 30 minutes. That would be awesome. All right. An ancient civilization on Pluto was known for its ability to manipulate space-time. While the historians explore their infinite corridors, you've noticed a strange set of physics-defying stones. At first glance, they seem like normal stones. They're arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. Sometimes the number engraved on a stone changes, other times a stone might split in two, causing all the other stones to shift over a bit to make room for their perfectly straight line. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones must each simultaneously change according to the first applicable rule in this list. Okay, here we go. If the stone is engraved with the number 0, it is replaced by a stone engraved with the number 1. Easy rule. If the stone is engraved with a number that is an even number of digits, it is replaced by 2 stones. The left half of the digits are engraved with the new stone, and the right half of the digits are engraved on the new right stone. The new numbers don't keep extra leading zeros. 1000 would become the stone's 10 and 0. Okay, got it. If none of the other rules apply, the stone is replaced by a new stone. The old stone's number multiplied by 2024 is engraved on the new stone. No matter how the stones change, their order is preserved and they stay on their perfectly straight line. How will the stones evolve if you keep blinking at them? You take note of the number engraved on each stone and the line your puzzle input. If you have an arrangement of 5 stones engraved with the numbers blah 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 blah, and you blink once, the stone transforms as follows. Okay, here we go. That one's 0. That becomes 1, correct? 1, odd number of digits multiplied by 2024, and that's that. Third is 10, split, right? Yeah, 1 and 0. Split 9 and 9. Odd, multiplied by 2024 to get this. Okay. After blinking once, your 5 stones become this. Here's a longer example. Okay, keep going. In this example, after blinking 6 times, you would have 22 stones. After blinking 25 times, you would have 55,312 stones. Consider the arrangement of stones in front of you. How many stones will you have after blinking 25 times? Okay. Ooh, deceivingly small. You know it's a trap. Uh-huh. Well, the parse function is super easy. New Clojure namespace day 11. Okay. Read? Is there a read string? Yeah. We're just gonna do this the lazy way. Get this, triple click. Def T. Boom. Let me make sure real quick, leading zeros or anything. Yeah, we're good. Okay. And so we need a step function. A step. It takes a state. Oh my goodness. Takes a state. And I think we're good to just linear scan this thing forward. Doing the replacements, right? Following these rules, of which there are not many. Like, I think that's going to be okay. Mapcat, because Mapcat is for when, 0 or more things can return from a single item. We have a number I. What's the easiest way? What's the easiest way to say how many digits in base 10 a number is? There's like a built-in for this, right? Like I don't have to. Really? Like that's. I mean, yeah. Mathlog 10. I think that's what I want. Well, only valid if it's greater than 0. Ooh. No, whatever that person's doing is crazy. All right, I'll just counted the string length. That feels bad. Yeah, this is what this person said, right? 1 plus trunk. Does that trunk? Yeah, though, this trunk. Log base 10. Oh, log of 10 base n. Yeah. But that doesn't work for 0. Well, we could just put a guard in. I feel like this will be faster than making a string and counting it. Maybe not, actually. All right. How many times do we need to check that though? Just once. Okay, so it's a cond. 0, 0, I, then 1, right? Equal, ooh, even, then it's, ooh, we need that string though if we're gonna do that. We do need this string. This stir form of this. State. Count of the stir form of this. If it's even, then we want to return take with split. Split at count divided by 2? There's probably a faster way using substir. Wait, no, this doesn't quite. Yeah. Okay, let's do this. Let's do parse long. There's a way to do this with math for sure. But whatever. I'm committed. Parse long. Right? And then the other half is another version of that from that to the end. Oh, this needs the S in it though. All right, let's do count as C. We only use it 10,000 times. And then we can let split divide by C2, so we aren't doing that multiple times. From 0 to split. And then from the split forward. Okay, assuming that works. I didn't want to do that. Assuming that works, then the rest is else times 2024 I. Right? Let's take a step. Don't know how to create I seek from long. Where did I go astray? What did I do to you? Let's see. Huh? That's a seek. Oh. Like this. Yeah, this is the one trouble with MapCat. You got to make sure everything you return is a sequence of some kind, right? That looks like the correct second sequence. Is that 2024 1099 2021976. Looks good to me. And they want after 25 would be that, right? So def in iterate, step, state. But how do we get the final? And just how many? What is the count of this? Is that correct? So 25. Take 25. After blinking 25, so that's 26, right? Count of the last of that, right? One, two, five, 6, 8, 1. That's way too big. Let's do 25 though. Maybe I misread that. No. Okay, let's do this real quick. Let's do something is wrong. Take 6 of parse t. Hang on, let's okay, now my second blink is wait, I need to I was looking at the wrong example. What? Hang on. Def T2. T2. Okay. Part 1, parse T2. 3, 6, 5. Yeah. But my initial take was it should be 26, right? I want everyone to note that I tried 26 the first time. Yes. 55312. 55312. Yeah, we're good. All right, def in. Copy. Paste. Part 1, parse of n. Submit. Boom. All right, the historians are taking a long time. To be fair, the infinite corridors are large. How many stones would you have after blinking a total of 75 times? This is gonna hurt, folks. This is gonna hurt. Guaranteed. How bad is it, team? Is it like, yeah, iterate doesn't work? Do you have to find like the shortcut way? That's how bad? Universe to end bad? So you have to find the shortcut? Like I can't just do 75 here. This is what is the big O of this one? Neutral, doubling. All right, so this is a power of 2 growth, but this is a neutral, but then these two, well, no. So yeah, it's a rough doubling. Power of 2. Aye. So this, but I believe that this won't work though. Like, just let my machine heat up for a while. Yeah. So you have to find the shortcut. Yeah, I mean, this is where I'm actually not incredibly good at advent of code. Like, how do you like? What's the shortcut here? This isn't gonna return. Um. It did it again. I don't know what this is. Huh. Reconnect. T prime, man. I mean, I might have to cheat. I don't know. What's another way of doing it? Is it to do with that thing I noticed a second ago? Like the number is only, this doesn't actually change the number. This also does not change the number on this step. The only thing that changes the number of digits is this, right? Think about part 1 of 125 and part 1 of 17. Ooh, I love this hint. Part 1, 125. Okay. Oh, not 2, part 1. And part 1 of 17. Hang on. And let's just... Well, 125 is not... Was this a power of the other one? And compare to T2. Oh, okay. So look at T2, and then look at them in isolation, basically. Oh. T2. Oh, I'm tracking. Wait. 125 was 19. They're just, yeah, of course, they'll just be summed. That's right. You can take each one individually and sum them up. It doesn't matter that they're all together. You don't have to do them all together, is the point. What does that... But I mean, okay, so you don't have to hold the whole thing in memory. Maybe that is a problem? Was that the problem? Because that hasn't reduced the amount of computation that you do, right? You do all the computation for 25 and then do all the computation for 17. That should get you closer. Okay, there is more to it. That's what I thought. But we can handle each number individually. That's a good insight. And then you can answer, you can do every... Like, you can keep handling things individually. Wait a minute. Wait a minute. 17 is... Do you have to keep a cache? Because every time you see a 1... Every time you see a 1, you're going to end up in the same spot, right? Like after 75 tries of 1, can I do 75? Okay. Not really. And it's going to kill my REPL again. Can't do 75 of anything. Can't do 75 of anything. Hang on. Let me look at this real quick. See. Let me do 10. Hang on. I want to see them lined up. Okay, so we know given a 1, in 2 steps it'll be 4. It'll still be 4. 7. See, I feel like if I knew the answer for 2024, I could slot it in here. But you can't straight compute the answer for 2024. So there's a trick to getting to it. And it surely involves the fact that it's recursive. Like, look at this. This. Look at that. The IDE will highlight it for me. Right, it's in a cycle, and this is just a subcycle of that. This is another. Those aren't the same because one is 2024 after 74 steps and the other is 2024 after 70 steps. I'm not tracking. I only did 6 steps or 10 steps. I did 10 steps because one is 2024. Like you. Oh, with 74 steps to the left. And the other has 70 steps left. Yeah. No, they're not the same, but like if you knew... I don't know. Yeah, I don't think this is the right line of thinking. That's just what I'm thinking right now. But in line 4, the 2s are the same. Yes, so yeah, if you knew for 2, I agree. If you knew for 2, you could slot that in here for sure, right? But like, I don't know, you can't do part 2 of 2 any more than you can do part 2 of 1. Right? Oh, I see what you're saying, because they have the same number of steps left. Yeah. Yeah, if you knew it, you could slot it in. I agree with that, but like, hang on, let me think. They have the same number of steps left. So for a given number... Oh, I see what you're saying. I see what you're saying, Maximo Burrito. Okay. Okay. So for a given number, with a given number of remaining steps... And is the secret to cache those? Is that the deal? Just like keep track of 4-2 if you have, 5 steps left or whatever. The answer is blah. When does it take off and like you cannot compute it anymore? It's not 75 exactly, is it? It's like it's got to be like 70 or something. Right? Let's see if I can compute 60 even, or 50. No. But you can do 26. Oy. Ugh. No, I feel like at this point you can kind of hint however much you want, but let me see what you got. Oh, I can't. Copy doesn't work. Copy. No. Copy. Let's see. F of 1 and 75 is equal to F of 24 and 74. Shouldn't this be... Oh, I have a question about this one, but then is equal to this plus this plus this plus this. Yeah, why is that getting decremented? Oh, at step 70. Oh, okay. For 1 at step 75 is this at step 74 is equal to 2024 at 73. Yeah. Yeah, but it ends up here. So this should be 72. 2024 at 72. I feel like I'm like right there, but I don't see it. Like I see like what you're saying, that these are equivalent. This should be, here, I'll fix it for you. That these should be of 274, 73, right? 20 plus f of 2, 4, 73, step 73. And these are all 2, right? 43. Oh my goodness. What? Ah, get me out. Replace with 2. There we go. But like you can't, I think I'm not quite putting together is like how you leverage this information. And I realize you could deal with each one individually, so I agree with that. Yeah, okay, so you memorize. Okay, so that is the thing, like you just memorize these and then you can do, but I mean, but that assumes, doesn't that assume that you can do one number? Like we can't do one number, we can't do 2, we can't do 0. Right? Like we can't take anything to the 75th step. And don't you have to be able to at least finish one so you get a bunch of these memoized? Can you do 0? Is that the answer? I feel like that's part of the problem that I'm not seeing. Is like, okay, well, how do you? We can memorize it, but how do you do the very first one? Fn of 0 equal. Oh, I see what you're saying. Oh, Fn of 0 equals to 1. Oh no. Fn of 0 is equal to 1. Well, is that helpful? Okay, so we got Fn of 0. Hang on, let me. So you're saying. Yeah, 0. Oh, any wait. Fn of 0 at any depth is not 1 though, right? It's not at depth n. Fn of 0 at depth n is equal to Fn of 1 at depth 70 whatever, right? Whatever remains, right? I mean, you do bottom out. Fn of 0 at step. Right. So it's f of 0 at depth 1 is equal to 1. Right? That's still not, yeah. You can't just memorize this computation and do it, right? Like that's still not going to work. You have to like do some closed form math on this, right? Or no? Like the problem isn't that I'm adding and doing string operations. The problem is the number of digits. So like memory jumps, it does work? You're kidding me. So like what you're saying is in theory, if I did this fast enough and this fast enough, it would be, if this were the same as a memory jump, then I could do it this way, is what you're saying? You cut down the branching. Right. Right, so you don't, okay. I think I'm tracking. So you're saying that, okay, if I have a step, right. Okay. I'm tracking. Okay. I kind of see it. So we do step star, right? But this one's going to take memo. And a state, right? And it's going to do step on the state. And return. Oh, wait. You don't want to just step. Okay, you want to. Slightly different, right? Right. You have to have the depth. I see that, yeah. I think I'm with you there. Okay, so it's either the memo of I. Oh, I see. But we have to track more stuff, right? Depth. At depth. Let's just hard code it. All right, 75 less the depth. So either you can grab I at the remainder of steps that we have, or you do the computation, right? And then for the return, is inkd state is s prime, and the memoize is going to be into memo s prime. Ooh, yeah. Wait. You want to do S and S prime? I forget how you do two. I think you can do it with sequence actually, but I don't want to do sequence. No, that won't work either. Okay, whatever. Do it like this. So for each one, ooh. Wait a minute. Oh, do you actually want to store the output? Do you actually want to store the output as a sequence of vectors? We don't actually want to. Okay, we want to update memo like here. Right, for this number, this is the output you want because you want to be able to do this addition. Ooh, so the memo has to do more than just a lookup. Like you want to recursively break down memo. You want to recursively hit memo with as you break it up, right? Wait, do you have to? Well, this will do it for you, right? It'll be just one more step, and then you'll go and do the memo. Right, but we do want the number of steps. I mean, not the step. We want to return a vector of things. We don't want to return just a number. But we still can't do it down here because we can't see down here what broke up into what. So either this, yeah, it needs to be like a transduce. We have to update memo as we go. Is the key, right? Let's see. I don't even know if we want to. I don't even know if we want to transduce. We might just want to straight reduce. Starting state S. Oh. As I don't know what we call it. Okay, this needs to be nums, arrangement, stones. What? Stones. And then this will be state S. So we're going to go over the stones, starting with state S. We get the memo out. Visit number I. Right. And here's where we say either get the value or compute the value. Let's see. If that memo is in there, some threader? So's? No. Aye. Win some. Win some. Then we want to say, hey, the memo is, we don't, yeah, we could say a so on the S, the stones, into stones. Wait, I guess the order doesn't matter. So this should be okay. And a depth of deck. Or ink. Otherwise, we need to generate it. Do this. All right, here we go. Memo of I at our depth D. Ooh, yeah. That needs to be in a vector. Memo of I at our depth D is our stones prime. And then depth. Ink D. There are certainly better ways to write this, but I think If I'm tracking correctly... What is going on? If I'm tracking correctly... I think this might answer it. So what you're saying is that with the... Whoopsie. With the branching that this is going to eliminate... that we can just do this now. What? I have 2 ripples going. Close. Let's see. Let's see if we can do part 2 of 1. Oh, well, this isn't gonna... This doesn't actually take... See, we take 75. You didn't track the stones, only the counts. Oh. So you... Oh. Yeah. I mean, that's going to be way less memory to do that. I'm gonna... Well, I mean... It'll just be pointers, but it will be pointers. A pointer is not 0. That's a good call out. So you're saying just the count of V. So this is not stones count. This is not stones. This is like stone counts. That's not a valid keyword. Oh, colon. Do refactor. Do refactor. Do it. Do it. Do it. Stone counts. So we just want to count the V right there. Like this number at this depth is that V. This number at this depth. Wait. Ay, ay, ay. Is the count of that. And then stone counts. Do I even need... Hang on. But we do have to... We do have to generate the stones, right? But we can drop them as we do them. So if we know that for this number it's... Do we... But that doesn't work. We do have to return the stones, right? You're saying just for the memo we can do the stone this, but for this needs to be stones still, right? Yeah, let me undo what I just did. Good lord. Yeah, undo that too. Okay, so you're saying... Yeah, what do we track though? So if you memorize the count, memorize just, hey, this is the, if we do a count right here, so this will be a count, and the number you get out of here is a count. We just like, add, I don't know. You just keep track of another count, right? Additional. Like that? And then... Wait, but it's going to be a list of numbers, right? Oh, no. It's going to be... Yeah. For this number, this thing, that is that many stones. Okay, but then we can just return this. We don't have to... Well, no, we're not map catting anymore. We're reducing. Oh, but you... Oh, this isn't going to work. You want to remove this one that you're working on. So I kind of want to map cat. I want to be map catting over the stones that we have. Okay, hang on. I just want to initialize this with nothing. That'll do it, right? Then this is fine. Because we have to put what this one generated into stones. So that on the next step we can come through and like check the memoization for it. But then we want to keep track of what we're getting out of the memoization as we go. So the final answer will be like, oh, I don't want to do it there. You don't want to just get the stones out and count them. You want to say, okay, how many stones are there right now? Wait. Don't go over any more stones. So this is what's going to cut it. Yeah, so when you get to the end, it's going to be, hey, what happens to still be in there plus whatever additional we need to get, right? I think you have to do some version of this. I mean, I could be wrong. Let's see. Do this, but then you can say, okay, let add is add, stones is stones, and you're gonna, let me slurp that. Slurp. And we're gonna do plus add count stones. All right, can I do part 2 of 1 now, which ought to be like the easiest. Not S. Yes, S? This returns a map. This returns a map. Oh, this was bad. Okay, this returns a map. This returns a map. This is a map. Oh, I'm not parsing it into a map anymore. Bummer. Here, Let's do this. Okay. I really wish it didn't do any of the wrapping. Cannot be cast to associative. String? Oh. Shadowing. I stir. Shift F6. I string. And this is back to S. Okay. Now it's got to be able to do one, right? Like that's like one has to be kind of instantaneous, I think, or else I did it wrong. Over the stones. These are the new stones. Can I do a smaller here? Let's try not 75. Aye. We want to do like a target depth. TD target depth. TD. But then we could do this. With a target depth of, I don't know, 10. Is this even remotely? Oh. Weird. I don't think I want to iterate. I just do take. I mean, does this look any like remotely close to correct? 1 to 2024 to 2024 to 2024. So 2024 depth 1 is 2. That's correct. And then so we got the 2024. Zero at depth 1 is not in our thing yet. Depth. I wonder what it... Why are we adding 1 right here? This isn't right though. This isn't 80, 90. Oh, this needs to be an empty vector. That doesn't matter though. This isn't 80, 96, right? Oh, this needs to be stones. Actually, yeah, we want to add nothing to it. To stones. Yeah, we dropped information. Okay, let's try this. Let's see. Not what I wanted. Okay, that's a pretty big lookup. Does it give a sensical answer for? Hey, we know the answer that it's supposed to give for depth. What? 26. Go to depth 26. Part 2 of 17 and 125. 55312, which I think was what it was. Okay. So we are getting sensical answers out of it. The question is, okay, at higher depths, what does it do? Yeah, I mean, that is part 1, right? But I can run our part 2 solution on part 1, I think. Yeah, it's just a bigger... Oh, I see what you're saying. I ran part 1. 24. Thank you, Maximo Burrito. 24, was that right? 24 steps? 25. Or 26, I think is actually what we want. Ooh, that might be one of the bugs that I need to fix. Okay, that's not right? It's just, there's no way to get to that either. That's just flat out wrong. That's not going to go down when I do that. Part 2. And if I do 27, it's not gonna... I mean, that's no way that's the right answer. So we already have a bug. Yeah, 26 is very close to the right answer, but it's not. So we have some kind of bug. 51,741. Okay, let's just run it. 26. Let's do this. $26. 27. Oh, is that the problem though? I think that might have actually been a bug. I think this needs to be take to the 27th with the target depth of 26. No. Wait, no, take 26 with a target depth of 25. Yeah. So this has to be looking one deeper than this, right? But that does now return the right answer. Okay, so now I can say 75, and this should go to 76. But I still don't think it returns. Yeah, it doesn't tell you what the practice answer should give. I don't think it's working. I feel like it should be pretty immediate if it actually worked. Yeah, it should be instant. Not gonna lie, like it's a little bit of like on faith that the memo is gonna cut down significantly on. Oh wow. Yeah. Okay, we'll look through this one more time. A memoized Fibonacci. Yeah. Yeah. Is that everything? Like, did you just use the memoize function in Clojure core Maximo Burrito? Yeah. That might have been the trick here. That might be the way. Hang on. Because we have this, and we just need to adapt this to take a... Right, a depth. Oh, no. This. Yeah, it killed me. It was like, you're done. Oh, I'm getting unsupported operation. Oh my, it's that Java thing, man. I hate that. It's literally this that you want to be memoized, right? But with a depth attached to it, like a target depth. Right. But you have to... Oh. You have to recursively call yourself. You have to recursively call yourself and return end stones. Wait a second. Oh. I've never tried to recursively call a memoize before. I mean, it's an atom though, so it should work, right? Like, so you're saying... Go until you know the number, until every number that you're looking at is in... Okay. Oh, I can just sum this, right? Wait. Yeah. No, this will work. This will work. Let's do this reverse though. Let's do it with that so we can use partial. Okay, this is making more sense actually, I think. So we have a calculation function that takes a depth and a target depth. This is let me rename this target depth. Right, you want to know how I at depth D, right? That's it. That's fine. Only the even length needs to oh, I think this might be a key thing that I was missing. But you still need to... Yeah, but you still need to recurse for these. But you're saying you don't need to sum. Right. I see what you're saying. So, like... Here. I see what you're saying. I see what you're saying. Now calc 1 at depth dec D. So, okay. Okay. Yes. Wait. If it's 0, I see what you're saying. Oh, yeah, 0. Wait, yeah. If it's 0 at depth, equals 1 depth, right? At 0 at 1 depth, then it's 1. Just 1. Uh-huh. Otherwise, if it's 0, then it's calc dec D 1. Any number at depth 0. Oh, depth. Wait, any number at depth 0. Yes. Not 1, 0. Got it. You probably saved me about 4 hours of bug right there at that spot, even without all the other help, Maximo Burrito. This one right there would have been like gnarly to get to. Okay, so yeah, at depth 0, it's always 1. If the number is 0, then we need to calc dec the D, right? If the number is even, then we need to calc dec the D of that plus yeah, this is way more straightforward. Calc dec the D of that. Otherwise, it's calc dec the D of this. Way more straightforward. Standard recursion. But with the important optimization of that, right? So with that, step 1 becomes, part 1 becomes calc state at a depth of 25. Right? That's what we're suggesting. Yeah, where state is a list, yeah. Is it not a list anymore? No, it is. Yeah, we're good. Or did I miss one? Were you telling me that I missed an error? We'll see. Persistent vector cannot be edited. Oh. Okay. Some of those. Right. Ooh. I would have gotten there eventually, I think. Okay, Stack Overflow. We are recurring after all. What happened here? At a depth D. Did we not bottom out? This is the problem with recursion right here, is that you can't just see what happened. But I guess we can print, but like, okay. For each number, calculate at depth 25. Depth 25. Deck. Every recursive call is decking the D. It should get to 0 eventually. The answer to that takes a 1. Print line deck D and I. Let's just see. How is it blowing the stack? Part 1 of this. It's not decking the D. 3, 5, 4, 3, 7. It should never go up. Well, I guess it could. It should get to 0 and then go back up, right? Because it's a depth first recursion. It should never like stop at 3 and then go back to 7. Like whatever it's doing here is just wrong. I don't know how though. This is a fairly straightforward recursion. Get a string. We get a count of that string. If the depth is 0, then return 1. If I is 0, then calculate at 1 less the depth for the number 1. Let me go back to the top. 17-1 2024. Yeah. 6. Oh, went to 0. That went to 0. Okay, now the other half. The other half goes to 0. Okay, got stuck in a cycle here. They just reduce plus with the X form, right? So it's going to go over each number. No, it's not a macro. It's not a macro. It's just a function that will go over each number and then call calc on each number, right? Ooh. If there was a... I gotta... Ooh. Should state be in the map? Should state... Oh, be in here? I don't think so. I mean, this should be the same as... Well, this is a transducer, right? Like, this should be the same as... What? Like apply plus, right? Those should be equivalent. These two. Let me double check, see if that works by chance. Maybe you're right. Maybe there's a problem in... No, I got the same. I think the problem's in calc. I think the problem is in calc. I mean, I'm almost certain the problem's in calc. Oh, we actually saw that the problem was in calc when it was printing in a cycle. Like, it's in this cycle here. This should never happen, right? That should drive to 0 immediately. So, okay, so at... Oh, no. Are you serious? Where's the DEC? Oh, good God. Oh, okay. In fairness, Haskell would not have saved us there. All right, part 1 of this 5312. Okay, yeah. Maximo Burrito catching my errors again. Okay, so that should be very fast for that, and I should be able to run part 2 on those 2 numbers now. Oh, what? Part 2 is not ported to our new stuff. Reconnect. Part 2 is a dangling pointer. Part 1, part 2 of state should be the same, but at depth 75. Part 2 now. Yes, some big ass number. So part 2 of parse in. Oh. Another big ass number. Maximo, you saved my bacon today, baby. Oh. Could I have come up with this? Let me think. I don't know. My level of belief, you saw it, right? My level of belief that Memoize would fix this was pretty low at the beginning. Like, I wasn't really recognizing. No, man, I think you're the only one in chat. There's 2 viewers. I don't know if the other person's being quiet or if it's a bot. But like, I really didn't want to believe that memoization would cut the branching so drastically, but I was like just dead wrong. I don't know why I didn't want to believe that. I mean, it makes sense. Like, you just got to build up a base and then it'll just recur down to itself. Like, this approach makes total sense. I think my headspace was so stuck, and this will happen in programming all the time. My headspace was so stuck in the previous solution that I had, which was like a more data structure oriented. So this is algorithmic, right? This is, do the recursion, do the recursing, and then add a memoized, not to taste, but to, as a flavoring on top of the recursion. But I was like, I wanted the data laid out in a certain way and then, beat the data to death. And I think my head space was there so much that I couldn't see that, yes, this was going to work as long as you do it like this. So, no, it was good. It was good. And this is actually we ended up in a very straightforward solution, which I'm going to guess if I go to day 10. Oh man, somebody at work is blowing me up. Day 10. Always at the top with Norman. Oh, I'm on 2024 day. Oh, 11. We're on 11. Oh, I never looked at day 10's things. Let's go day 11. Oh, I'm in the thread. Day 11. Oh, there's day 11. Okay. Here we go. Norman. Boom. Boom. Yep. Literally Norman solution. Big surprise. Let's see what we got here. Yep. This is the way, folks. Frequencies. Frequencies. What? Okay, yeah, this is just that string stuff that I didn't feel like doing. Oh. Okay, this is their form of memoization. This is what I was trying to do. Wait, I think. Rock freak. Rock number to old count. Split number is step the rock number. So get the next number from this. Put into here. How does this work? How's this work? Old count. Right, so get the current state. For each item in the current state, which is the rock and whatever old count is, take a step that returns. And so for each thing in the split, this is mapcat, right? So this would be like that 1024 or 1 to old count. And then add them all up. I don't understand how this works. How are they cutting down their iterations? Are they cutting down their iterations? Okay, this is Erdos. So he is somehow. How does this work? Is this fast? What? What? Wait, how's it called though? Okay, you gotta do some incantations. Reduce plus. Hang on. Let's do 17 to 125. Oh. How does this work? Okay. Step. Huh? Log 10? Let's see, Math Pal should work, right? Is there a math log 10? There is. Clojure math functions. 8 milliseconds. I thought I tried this and it was too slow. Maybe I did it wrong and resorted to memo. Yeah, this is what I wanted to do, but I have no clue how this works. Right? Like, how does this, like, how could, so this is literally doing the same thing that we did without, yeah, each level is stoned to count, but he's not reading from this. Oh. Well, no. This is what we had initially. If O to N, then 1 to N. If O goes to N, then 1 goes to N. Even, add, left count. Right, right. I mean, that's what this will... Let me see. Well, this will generate left count, and then as a separate hash map, right count. But he'll add them together. Wait a minute. Calculate. Okay, calculate 17 frequency of 1. Oh, what does that do? Let me just do this. Let's do this. Let's make sure I'm not crazy. This is going to turn hash out to 1, right? Yeah. Yep. Take 10. Alright, so he's building up the memoization. 17 at depth 1 is... No, it's not depth, it's count. 17 goes to 1, 1 goes to 1. Oh, but this is the depth. This is the depth. Right? So I mean this kind of makes sense. Okay, at depth 75, get the values and add them up. I'm still not track, but it's not using this as a memoization. It's not. I mean, I guess it's starting from here, but it's just using that to calculate. It's not actually looking inside a rock freak at all. Right? So it's not cutting any branching. If even, add left count and right count. Yeah. I mean, I see how it works, I think. Let me see. Yeah, no, at depth 75, like, this appears 3 times, basically. But this just does the calculation, right? It's not memoizing. Am I crazy? Is that right? It's not sidestepping anything. Why does this work? Not by tracking the counts. Right. Let me look at the history of this real quick. Whoopsie. History from local history. Let's go back. Right. So what we were doing 2024. Yeah. Yeah, exactly. Well, it's not preventing that either, right? Let me look at this. It's not preventing you from calculating it twice. In fact, it expects you to, right? It says it occurs. Oh, but it's not. I think that's the point. It's not calculating it. Okay, I see what you're saying. So what we were doing was doing the calculation up to the depth. Right. Right. But he's just saying, instead of doing the calculation and returning what the next step is, just say how many occurs at this level. I mean, yeah, just how many of this occurs, right? And then generate the next map of like what occurs on the next step. How many of those happen, right? So he's memoizing, which will collapse it. I see. Yeah, that's it, maximum. Like, so, yeah. That collapses the 2 down to 2. So you actually, it's a navigable space. You're not doing 2 twice. Okay. So that cuts down. So it's just 2 different ways of cutting down on the branching, right? This one cuts down by saying, hey, what is the depth? What is the value of this at depth D? And then knowing where the end point is, right? So I'm going to cut down on branching by tracking the end result at a depth D, which is actually harder for me to see that it will work. I see that it does work, but it's harder for me to see that it will work as opposed to this, which is like, yeah, like you said, for 2024. Let me get this so make sure everyone can see. 2024 will be represented. I didn't. Copy doesn't work. Copy. Will be represented like this, right? This is 2024 with all the bits that matter, which is that there are 2 2s, 1 0, 1 4, right? That's the only thing that matters. You aren't going to go down this traversal again. That's where you're cutting down on the branching. You cut the traversal by a quarter for this iteration, but that builds as you go, right? 25% on iteration 2 is pretty good, right? And I think it's only going to go up. Interesting. Man, Erdos is so good. Erdos is so good, man. I can't believe this works, though. Yeah. Somebody else had the same problem. Every time I see an awesome Erdos solution, like, other people are like, wait. Yeah, exactly. Exactly, Alex. Friend of the show. Right, it reduces the number of, repeats. It cuts down on branching in a way that's slightly different than what we did, right? Shady with the memoized recursion. Same exact solution. I wonder what he means since it only operates at that level. Oh, yeah, no. Yeah. I think I agree with Shady. Like, it's not obvious to me that it's still not completely obvious how it's cutting down because it depends so much on the level that you're at. It obviously works, but this clearly just collapses every space down to a more compact representation. How's Helman do it? Yeah, same thing. Minimize it. You should benchmark that, Shady. Are you gonna do it? Does he come back and benchmark it? No! Shady! Come on, man. Yeah, okay. So my takeaway from this one is that number one, okay, if it's a recursive thing, don't be afraid to go recursive. Don't stop trying to do data when it's recursive, right? But I mean, this one's a data-oriented solution. The other half of the thing is like always, like if they want a count of something, don't do the stupid caveman thing of like, okay, I just gotta make a version of this that does exactly what they say. Like, do exactly what they're saying. This is not a tried and true method when it comes to advent of code, right? It's hey, what information must you track? And in this one, you have to track just the counts that you're on, like the counts of each. Yeah, really, all you need is how many stones are here. And if you can find a shortcut to get to that, you're going to be better off. But yeah, Erdos, see, this is where my brain was like falling apart, right? Erdos, I was like, we only need to keep track of the counts, yes. But we also need these numbers in order to know what the next step is, you know? You need these numbers. You can't not track those numbers. And Erdos found a way to do that well, right? Track these numbers and the counts and nothing else. Oh, that's so good. So good. All right. That's enough for me for today. Thanks for stopping by. It's been fun. It's been good. Do I dare try day 12? Yeah, let's just say I'll be here tomorrow. I'll be here tomorrow. We'll try day 12. We'll see how it goes. All right. Thanks, everybody. Catch you later.